I'm Sara. I'm working at Delphix, and I'm going to talk about a ZFS performance optimization with regards to how we delete clones. Through my talk, I'm going to talk about how we delete clones now and why it can be really, really slow, the fast deletion algorithm, and then changes to the algorithm we've made to basically make it more scalable within the ZFS ecosystem. And then I'm going to talk about performance gains and basically why this is an awesome, awesome thing. So clone deletion. So as you know, clones are mutable copies of existing data sets. You take a snapshot, which is a frozen version of the data set, and then you can make a clone, and then that means that you can change things based on that snapshot. Copy on write means that creating a clone is as simple as pointing to the root of a given snapshot. So creating a clone, super fast, super inexpensive. Throughout the course of the clone's lifetime, it diverges from the original. So the user writes data, they delete things, they change things, and the clone originally was sharing all the data blocks with its snapshot, and then gradually develops data blocks of its own. So deleting a clone requires determining which of these blocks are still shared with the original and which blocks belong to the clone specifically and should actually be freed. And the basic strategy of this is to iterate over the on-disk tree and ignore sections of the blocks based on birth time. So here's an example. The green are the blocks that pertain to the clone, and then the blue is the underlying data set. So in some cases, this isn't too bad. One example is a contiguous write. So down in the bottom are the blocks written by the user, and these are all contiguous. They take up one contiguous chunk of memory, so not that many indirect blocks have to be modified and traversed to find things you want to delete. On the other hand, there's no rule that your writes have to be contiguous, and if you have sparse writes all over the place, then you end up basically having to touch every part of the tree when you want to go and find what you have to delete. This can be really expensive because you have to read in your indirect blocks and say, okay, where are the other blocks? When were they modified? Should I actually care about them? So the kind of takeaway from this is that in the worst case, deleting a clone is proportional to the original size of the underlying database. It doesn't matter that you only made 4 tiny changes to the clone. If you made them in a scattered enough place, your deletion cost can be proportional to whatever that clone was based on. So that can get really costly. This isn't like a super dramatic example, but you can see these are all underlying data sets of varying sizes. The amount of data that was written to the clone is fixed. It's 500 megs. But you can see that 500 megs of writes looks like very different deletion times depending on how big the data set is. And the red bars are for random writes, and the green are for contiguous, so you can see that random is worse than contiguous, although contiguous can also get pretty bad. So at Delphix, we've seen users kind of run into this situation where you may have maybe terabytes of data, you make a clone, you make a few small changes, you go and delete it, and it takes you 45 minutes. So it's a problem. All right, our algorithm. So the basic premise is to change this underlying issue that deleting a clone means caring about what the original data set looks like and the size of the original data set. What we want to do is keep track of the clone-specific writes and deletes as they occur, so that when it comes time to delete them, we only have to care about the actual changes that happened on the clone. So the premise is to store them in a live list. To delete a clone, we just have to process each element in this live list. Work is proportional to the number of writes to the clone, not to the size of the data set it was based on. So here's some more detail on this live list algorithm. So we need to have this data structure, and we are going to enqueue block pointers that were both allocated and freed on the clone as the writes occur. We need both the allocs and the frees, because if we only keep track of the blocks that were allocated, over the course of the clone's lifetime, those blocks might have been freed naturally by the clone, stuff that happened to the clone, and we don't want to double free them in the end. So when we want to delete, we need to determine which were the not yet freed blocks, the ones that are circled in red. And the way we do this is we're going to step backwards through the live list, insert frees into an AVL tree, check for memberships of allocs in the AVL tree, and then based on that, you'll know if you'll have to delete them. So little more step through of how that works exactly. We start at the end of our live list. We have this handy invariant that all frees of a block will happen after it's allocated. So that's why you can go backwards. We see a free, we keep track of it in our AVL tree. We see an alloc, and we check if it's been freed. It hasn't, so we're going to keep track of it as something we actually do need to free. We see another alloc, oh, it's already been freed. We ignore them both, store our frees, and then check for memberships of the allocs. This alloc has already been freed, so we ignore it. This alloc has not, so we free it, and this alloc has, so we ignore it. So that's basically the core of the correctness of this algorithm. We have this data structure, we process it, we know what we have to delete, and significantly, this is proportional to the things that have happened to the clone, not to its data set. So, where are we now? This algorithm was implemented this summer by a Delphix intern, Sara Gopal, and she saw like really good performance improvements, and signs were looking good. There's still some things that we want to tweak to this algorithm to make it more scalable. One, as you might have noticed, is that the live list can grow arbitrarily large. Basically, if a clone lives a long time, a ton of things will happen to it, and this data structure can get really, really bloated. This is also something that's tricky to incrementally destroy. I'll talk about that a little bit later, but the kind of pattern of incrementally destroying something and not doing all of your work in a single transaction group is an important pattern within ZFS to keep things basically flowing, and to not spend too much time deleting and like prevent users from actually doing stuff. So the next step to try and address these issues is to break the live list into smaller fixed size sublists. So the idea is that if we can make the guarantee that each sublist contains both the allocs and the frees for a given block pointer, then we can process these sublists independently. So in the first sublist, if we want to delete this, we don't want to care about anything that happens in the other sublists because we only want to load one into memory at a time, instead of loading a giant amount of stuff into memory, an arbitrarily large amount of stuff into memory. So one question is, how do we guarantee that matching blocks are grouped together? And the solution to that is to group them based on birth time. So basically this sublist will be all blocks that were born in this transaction group, and then the next one can be blocks that were born between these transaction groups. And one of the key ideas is that we're creating these extra sublists dynamically. So as we run out of space in one, we create another, and that way we don't have to like pre-allocate how many initial sublists. Another question is, how big should an individual sublist be? Because of the transaction group grouping, we know that the smallest it can be is the number of writes that happen within a given transaction group, so that's kind of a lower bound. That's obviously like not fixed. And then an upper bound is the question here. So this is still something that hasn't been like fully decided upon as one of the main tunables for this performance feature. But basically what we're doing right now is what's the smallest fraction of RAM to use in a delete. So we're doing about 1% of RAM right now, and a sublist can have about 500,000 entries. So we solved that problem of arbitrarily large amounts of memory to read in when we delete. The other nice thing about this is this presents a handy interface for incrementally destroying something. If we can process these sublists independently, then we can destroy them between transactions, in different transaction groups. The other handy thing, or at least thing to consider, is the concept of asynchronous destroy. Mark maybe mentioned this in his talk, but the idea of doing a lot of your destroy work in the background is pretty appealing. So what we wanted to figure out is what part of this delete algorithm actually does need to be in syncing context and which part can be done by a worker thread in the background. So when we call ZFS destroy clone, we'll basically enqueue this clone's ID as something to be deleted, and then we'll signal this worker thread that will do the work of loading in the live list, doing the algorithm with the AVL tree to figure out what we actually need to free, and then it can call a sync task, which will actually do those deletes. And so this has the benefit of, again, like pushing this loading in work to the background and making sure that we're only really doing critical work in the syncing context. And then this lets us do it incrementally as well. So where are we now? Pros, we've limited how much memory is loaded in at once with the sublists, and we can delete things incrementally and more quickly. So a con, you might have noticed that the number of sublists is unbounded. We still have this problem of we're using kind of arbitrarily large amounts of disk space throughout this algorithm. If a clone lives a really long time, we can have a ton of sublists. This gets expensive in two ways. One is just disk space. We're just using up a lot of memory that we don't necessarily need to use. And the other is that the more sublists we have, the cost of actually modifying and updating the sublist throughout the course of the clone's lifetime becomes greater. So every time you write to a clone or you delete a file or you move something around, we're going to have to interact with this live list. And we don't want to make that interaction so costly that we're actually degrading the performance of writes and things to a clone. So the more sublists we have, the greater the number of IOs we have to do to propagate these changes. In the original case, back when we had one giant sublist, you just append to the end of it. That was it. There was only one place to put things. But when you have a bunch of them, the cost of insertion of a bunch of different IOs is greater or a bunch of different block pointers is greater because they're spread over different areas. Cool. So the next idea is condensing. After a block is freed, the live list is now containing irrelevant information. So for example, in this one, we have block pointer 1. We know that we've freed that block, but we're still keeping this information around. We're still keeping this history, even though we're not actually going to do anything with it when we're actually deleting the clone. So the idea behind this is before we actually delete, we can condense. So we basically use the exact same algorithm we use for deletion to determine which are the still living block pointers, which are 2 and 3, and we just get rid of the ones that are no longer alive. So that reduces the amount of disk space we're using. We're no longer storing these block pointers that we don't care about. Can we reduce the number of sublists we're using? Well, since we've compressed these things into a smaller sublist, if they're under half of the minimum size of or maximum size of the sublist, then we can merge them together and reduce the overall number of sublists. So here we've deleted we've deleted everything with a corresponding free, and then we've merged it together in one sublist that basically stores information more compactly and is information we actually care about when we're deleting. So in general, what have we done? We've made the work of deleting a clone proportional to the number of writes to that clone as opposed to the size of the data set. We've limited the memory that we load at once. We now have tight control over what happens when we delete. We're not going to load in tons and tons of memory when we delete something, which was an issue with the original live list algorithm, and we did that using sublists. The sublist paradigm also gave us a strategy for incrementally deleting sublists and asynchronously destroying them. And then this condensing, merging strategy gives us the ability to limit the number of sublists by periodically condensing them. I should have mentioned this in the earlier slide, but the condensing strategy kind of gives us a lot of questions. In an ideal case, we would never store redundant information, but loading in everything to get rid of redundant Alex would be pretty costly to do forever. So we probably want to have a kind of background worker thread that's periodically condensing when it can. So how often should we condense? When should we condense? These are all questions that we don't know yet, and will be interesting to kind of try and figure out how the system acts under different workloads. So here's some performance numbers. These numbers are from Sara's internship, her implementation of the live list. So these are kind of just the vanilla one big live list. This is the contiguous write case, which is where we saw kind of the least concerning behavior from the original delete strategy. So in this is basically just a small example, but turns out we have actually reduced the number of IOs with this live list strategy, so deletion is a little bit faster even in this contiguous write case. I said we've deleted the number of IOs. We've reduced the number of IOs for the deletion case, but we've also added some IOs which happen while we're adding things to the clone, right? We've kind of spread out some of this work, right? Instead of just doing all the processing and all the deleting work when it's time to delete, we're kind of like paying it forward by keeping track of what we're going to delete, which is handy. So the most improvement is really dramatic. You can see in this case we have 500 gigs of data, which is the underlying data set, 500 megs of sparse data were written to it, and it took 46 minutes to delete with the old method. And with this method, it takes 30 seconds. It's like 100 times improvement. It's pretty good. So this, again, is the sparse case, and that's where we see, like, it's also really interesting to kind of look at this, like, small data set, 500 gigs. We can see that the live list deletion time stays relatively contained and relatively, like, constant because we're keeping track of this data as it happens, because we're doing a delete that's proportional to the size of, to the number of writes we do as opposed to the size of the data set. So yeah, things are looking really promising with this. And yeah, so live list clone deletion gives us really dramatic performance improvements, especially in this worst case. This worst case scenario can show up when people have really big data sets. They're creating clones, they're deleting clones, they're trying to make more clones, and people just, like, they think they've deleted something, but they can't actually create a new thing because the blocks have not been reclaimed. So speeding up this is really good for high usage systems with, like, really big data sets. And then we saw these tweaks that were made to make the algorithm more scalable. These are really interesting because we were balancing things like how much memory do we want to sacrifice to this live list system? How much work should we spend optimizing it throughout the course of the live list or the clone's lifespan? And yeah, so it's underway. Hopefully it will be coming soon to OpenZFS. So yeah, I just wanted to say a quick thank you to Sara, who did a lot of the original work on this project, and to Matt and Seraphim, who helped me out a lot at Delphix. So, questions? Yeah.
So, Sara, this is great. Unfortunately, our use case is the exact opposite of this.
Uh-huh.
Small data sets, very, very long-lived clones, arbitrarily long-lived clones that we then don't care about deletion time.
Uh-huh.
Will this be optional? Will we be able to, because we'd like to be able to broadcast that intent when we clone that's not something that would benefit from this.
Right. Yeah. Right now we have this set up as, like, a property.
Perfect.
So yeah, you can enable it or disable it.
Please reiterate the
Oh, sorry.
No problem.
Yeah. The question was, is this feature going to be optional? Because there are cases where the old delete method is fine and you don't want to keep track of extra data as you go. Yeah.
So also clearly in the clone promote piece, you must have to do something a little special here because you're not flipping something that was a clone into a data set and something that was a data set into a clone.
Yeah. Yeah, we're actually, so the question is, in the case of clone promote, how do we handle this? Because you're basically changing the roles of these and the relationship between these data sets. So currently we are not supporting this feature for promoted clones. I can't super see people, but yeah.
Sorry, I probably didn't catch the explanation, but exactly how do you resolve the inter-sublist dependencies? So when, for instance, a block is allocated in one sublist, read in a far later one, how do you resolve that? Or is that done simply by way of the condensing mechanism?
So the question was, how do we resolve the fact that sublists need to be independent of each other? Namely, all Alex and all the frees for a given block pointer should end up in the same sublist. So the way we do that is we group the sublists by birth time. And so a block pointer that was created will have a birth time, and then when it's freed, it will have the same birth time as its created copy, because they're, like, the same block pointer. So when we insert them, we basically index by birth time. And so if something's created in transaction group 1 and then freed in transaction group 9, it will still have the birth time of 1, so we can just insert it.
So sublist
Yeah. Yeah, that's a kind of like interesting feature because like all Alex will go to the like current sublist that's like the newest one, but freeze can go anywhere. Yeah. Yes.
Two questions. One, so where is the live list stored on disk? Is it in the clone itself, or is it in the modes?
So while the clone is still in existence, it's stored within the clone itself in its data set. And then once it's deleted, it's moved to the MOS for like pool-wide access for deletion.
Okay. My
Oh, and I forgot to state the question. But the question is, where is it stored? Where's the live list stored?
My second question is there a reason that, for instance, the space maps seem to have a lot of the same functionality? They do condensing, they are append only, and things like that. Is there a reason why they were not used for this?
Yeah, so the question is, why didn't we use space maps? They share a lot of similar functionality. So I know space maps were definitely considered for this strategy, and I don't know the details of why they were not decided on. Maybe Matt can address that.
So there's kind of two reasons. One is that space map is specific to a VDEV, which is something that actually we are working on changing. And Sara is going to have a talk about that. That'll touch on that later on. But the main reason that we didn't do is because of dedupe blocks. So when you go to free a dedupe block pointer, you need the checksum rather than the location on disk. The space map just stores like the location on disk. So we considered actually doing like a hybrid where you have like both the block pointer, like what Sara talked about, and then also a space map. So like every one of the sublists would have like a list of block pointers and a space map. And like mostly you'd be able to use the space map, but if you're using dedupe, then those would go into in the list of block pointers. But we felt that it was just like too much complication to use in the short term, and like the performance wins were so huge that we were like, seems good enough.
Cool. Any other questions? Yeah.
Yeah, did you look at the case where the clone approaches the point where most of the blocks are not shared with the parent snapshot, and is it still beneficial in that case?
Yeah, so the question was, have we looked at the case where a clone has almost completely diverged from the parent, and whether or not this strategy is still beneficial? So we haven't looked at the performance on that in detail, but we did see that like the contiguous write case still gave us performance gains. So in the case where I'm just contiguously overwriting an entire clone, we would still expect to see some performance gains, kind of gains on the scale of what we saw here. So probably not huge, but yeah. Other questions? Nope. All right, cool. Thanks so much.